And I want to remind you of the challenge I set you earlier on for the beginning of the plenary this afternoon, picking up what we heard from Ricardo about what is preventing you from engaging. Is it the money? Is it the willpower? Is it the mindset? What is it that needs to get you across the start line for many of these applications and improvements that we're sharing with you, both the first 4 this morning and then the second 4 now? Adil, welcome. You're Sustainability and AFR Director for Simon del Atlas.
Yes, CIMENTS.
Yeah, welcome. And do you need some slides?
Yes, I have prepared some slides.
Good, excellent. Okay. If you can keep your remarks to 10 minutes, it would be helpful.
Okay.
Thank you.
Okay, so good morning, everybody. So I am going to talk about our little experience about LC3. Just to put you in the context of our experience, I will start with the short history about CIMENTS. So CIMENTS, it's a young company which was founded in 2007 in Morocco with 2 integrated cement plants. And these plants were commissioned in 2010 and 2011. And then afterwards, we started the development within some countries in Africa with grinding plants, essentially. And then we are now launching the construction of a full integrated cement plant in Senegal. The construction has already started.
So you're going to talk about will LC3 fulfill its potential? Then we'll have coffee.
Yeah.
We're going backwards. You need to do the top big green arrow, the one in the middle.
Okay, thank you.
Voila.
So we have a sustainability approach based on a model with the 5 pillars. And as you can see, the climate change is at the heart of our sustainability approach. And since the starting of our company, so we have did a lot about decarbonization. So I think that we have done almost what can be done to use the 30%, the easy 30% reduction of CO2 that we were talking about yesterday. So we have invested in alternative fuels. We have used mineralization. We have we are using also renewable electrical energy for both of our plants. And now we are we have the project to build a pre-treatment facility for industrial waste in Morocco. So here are the levels of the reduction that we all know. So regarding the energy efficiency, so we are, from the beginning, we have considered the energy efficiency by choosing the right equipment, like high efficiency coolers, frequency variators for all main drivers. We perform also regular kiln heat balances. We have dedicated people to perform these heat balances and to optimize the process from the energy point of view. And we also got the ISO 50001 certification, which treats about the energy management. Regarding alternative fuels, so we did, since we started the strategy of alternative fuels with CIMENTS in 2013. And so we have invested a lot in equipment for the alternative fuels injection. And we have already one pre-treatment facility of waste in our Benimellal plant. And we have started using also sewage sludge, dried sewage sludge, and shredded tires and industrial waste, and also some kinds of biomass. Regarding the renewable energy, so we have contracted with the main suppliers in Morocco for wind energy. So all our plants are fed with renewable wind energy. For clinker factor, so from the beginning, we were using fly ash as a supplement for clinker, and we have also started a mineralization for our clinker. I think this is something that not much people talk about, but it's important and it's an easy way to reduce the clinker factor. And for our Scope 3 emissions, we have worked mainly on our logistics. So we have connected our main cement plant to the railway station, and we are using also, we are trying to optimize the transport of wastes by using moving floor trucks. And the results of all of that is the thermal substitution rate, which is about 33% by the end of last year. Regarding renewable energies, we are achieving 80% of our electrical consumption that comes from wind energy. Our clinker factor is close to the normative limit in Morocco. And all this gives us a 16% reduction of our CO2 emissions. So now, regarding the next steps, we have a roadmap under development, CO2 roadmap, which will be finalized by the end of this year. And we plan to submit this roadmap as well as the targets to the SBTi next year. We believe that the routes that we have explored so far right now have reached their limits. So now I think that if we want to have more results, we need to do a step change in and to explore alternative and new routes. So one of these routes will be the further increase of the TSR. We plan and we would like to increase our TSR to 50 or between 50 to 60% by 2028. This is a big challenge. I have started the discussion before, but because the supply is a challenge, but also the technical point of view is also a big challenge. It's not easy to say that we will use alternative ways. There are technical limitations, combustion problems with emissions, problems with chlorine, and we have to overcome all these kind of problems. LC3 is considered as a high potential solution for the mid-term targets until 2030. We consider the LC3 as an intermediate solution before going to further steps like the CCUS. So right now we have 4 LC3 projects under development, and we have 3 photovoltaic fields under development in some countries in Africa. And to finance all these projects, we are setting up a green bond, which will include all our green projects. So why LC3? LC3 because we believe that it can have a significant potential because on CO2 emissions reduction. We all know this potential. It's between 10 to 30%, and it depends on the clay availability, the quality of the clay, also the normative constraints, and also the actual level of clinker factor. Having been at 90% clinker factor, it's not like at being at 70%, for example. And also, we believe that it has a good potential because it allows the convergence of both environmental and economical issues. It allows the increase of cement production without increasing our clinker capacity. The capex for calciner for clay calcination, it's much lower than of full clinker lines, and also because in many regions, especially in West African countries, there are no deposits of limestones, and this solution could be the only solution to avoid or reduce the clinker importation to produce cements. So the LC3 projects should be managed as in a structured way as all bigger projects. So we have identified 5 phases. So the first one is the opportunity identification. We start projects when the environment is okay for this project. So it depends on when we have a potential on the clinker factor. If we expect some evolution of the normative aspects that will allow lower clinker content. Afterwards, the second phase, it's the clay disposal. So this is a point which should be taken with much care, because the clay is the key factor. If the quality of the clay it's essential, especially the content of the kaolinite. And then we have to be sure about the content of the clay, and we have to perform very good characterization of this clay, to perform laboratory trials and also industrial trials. And the outputs of these trials will be the input for the next step, which is the feasibility study, to have real figures to base this feasibility study. Afterwards, we have to secure the clay reserves, and then we can do it also in parallel. We have to select the appropriate technology depending on the available technologies, but depending also on our industrial tool. From our little experience about the LC3, we have been able we can share some practical considerations. So the first one is there are some impacts on the LC3, impacts on quality of the cement, impacts on the emissions, and all these impacts should be addressed from the beginning and the starting of the projects. The second thing is that we have to approach the constructors of the LC3 projects very early in the projects, because the clay quality have to be validated, because there are some color issues that arise with the LC3. And these color problems can be addressed in the process of the clay calcination if they are taken into consideration from the beginning. There are also some emission impacts depending on the content of the clay. If there are organics on the clay, we can expect to have CO2 emissions in the stack. And also because the contractors have pilots, and these pilots are very helpful to perform industrial trials. There is the third issue, which is also important, is the storage and the handling of the clay, because we are talking about handling 100% of clay. In many countries, this clay can have huge humidity, and it can be really challenging to manage this clay. The alternative fuel usage in the process of the calcination is also an option that have to be considered, because it impacts positively the CO2 balance of the project. And also, care should be given to the appropriate selection of the technology. So I will finish my presentation with some key learnings. So the first one is the clay deposit, which is fundamental. So we should have enough reserves. The percentage of kaolinites is very important. It impacts directly the clinker content in the cements. And the percentage of kaolinites, which should be more than 40%, it's very important. We have to take also into consideration other aspects of the clay, as I mentioned before, the organics contents, the chlorine contents, sulfur contents, and all these contents have a direct impact on the emission. We are all hearing about numbers like 30% reduction, 40% reduction. I even heard about 50% reduction. We have to be aware that these numbers are potential, and the reality may differ strongly with this number, and will in fact depend on many factors. The first one is the clay quality of the clay, the actual clinker factor, the normative limits, and also the possible use of alternative fuels or no. We have to anticipate also the impact on the cement characteristic. So I mentioned before the color of the cement. So this clay process gives a reddish color to the cement. The process technology is able to reduce this impact of the reddish color if we take into consideration at the beginning of the projects. This impacts also the operating costs, so we have to be aware about that. And there may be also an impact on the water demand on the cement produced with clay calcination. So this is something that have to be managed with the clients, etc. And also, I will finish with that. So the normative limits can be the real obstacle for the development of the LC3. So I think that we have to work all together. The National Cement Association, regional and also worldwide cement associations need to be involved and to influence the government's decision to move forward with low carbon cement norms.
Thank you, Adil.
Okay, I have finished. Thank you.
Let me ask you two questions. Does anyone want to come in as well? We'll get the microphone to you. I was very struck by two phrases: high potential solution, LC3, high potential solution, and additional cement production is possible without increased clinker capacities. And we're going to hear from Francisco shortly about clinker. But in the end, although it's not perhaps the right phrase to use in Morocco, you're using greenfield sites. You're starting from scratch. What about the legacy cement producers and the prospects that they have for LC3? How does what you've discovered apply to those who've already built substantial infrastructure and want to change?
Our projects are not concerning new plants. They will be implemented in existing plants working since many years. And for this reason, I mentioned that the appropriate selection of the technology for clay calcination. So it has to take into consideration our existing grinding cement facility, because there are many solutions. Some of the solutions need to inject the clay in the separator. Others need to inject it in the entrance of the mill. And I think that this is a technology that can adapt to the existing facilities.
But I'm quoting your numbers here: 33% thermal substitution rate, 80% energy is renewable,
yeah.
Clinker factor, and a 16% reduction of CO2 emissions. Are you saying that everyone in this room could do the same as you have done?
There are some actions that depends on us, but there are some actions that depends on the environment. 85% it's the part of our renewable energy. We did it in Morocco because in Morocco there was a political decision to promote renewable energies. So if you are in a country where there are no wind fields, it will be difficult to achieve such results.
But what I'm picking up is what Ricardo said at the beginning of today. He wants to know why people are prevented, why companies are prevented from making the big steps that are necessary. Can you see why, based on your experience, this should prevent people?
I think, in my perspective, lots of things. We have to consider advanced countries. Advanced countries, I think the things are easier. But in developing countries, like in Africa, for example, we are depending a lot of the political issues and the government policies. For the waste, for example, we were talking with Dirk about 60% thermal substitution rates. I don't think this is realistic in Africa, because in Africa, right now, it's easier to put the waste in the landfill, and it's cheaper to put the waste in the landfill than to have it treated and used in cement kilns.
Now, probably like most people, I'm not familiar with those locations. Mm-hmm. Where are they? Are they reasonably close to habitations, or are they in the desert?
They are not in the desert. They are close to big cities.
Okay.
Yeah.
So there are already railway links.
Yes. For example, there are railway. But the plants still have to invest to connect to the railway. We have about 30 kilometers to invest in the railway.
All right. Anyone quickly want to come in? Please, one question over there, microphone, and then we'll move on immediately to Francisco. Please.
Good morning, Mr. Mohammed, and thanks for your wonderful presentation on LC3 CIMENTS. My question is specific to one of the challenges that you mentioned about storage and handling of clay material in warehouse. Could you please elaborate on that? What is the challenge, what you face? Mm-hmm. Specifically on the challenge side, you mentioned one point on the...
What is the challenge for clay?
The clay,
yeah.
It's when the clay contains high moisture, it becomes viscous. And then the way to manage it is very different from the limestone. So the handling system have to be designed from the beginning to manage this clay. Otherwise, you will have blockages in the conveyors. The bins, for example, for storage, have to be designed accordingly to these constraints. Otherwise, there will be blockades.
Adil, thank you. I'm going to have to stop there because we started 15 minutes late and it has implications for lunch. So okay. Thank you very much. Stay where you are for the moment. Okay. Francisco Canpea, who's from the Christian Pfeiffer Maschinenfabrik, talking about reducing clinker. Francisco.
Hello to all of us. Well, first of all, thank you for organization. I think that is a very great meeting that we're having here, very open talks. I like that. Normally, I'm used to participate in many conferences worldwide, and honestly, I'm not seeing this kind of open talks as I'm seeing here, so it's very nice to participate here. Good. The topic today from my side is we are, as Christian Pfeiffer, experts on grinding and separating technology, and beside all the fields that we are trying to go and to focus for the next future for arriving this 1.2 DS roadmap, is trying to focus in something that you were talking here openly, and I like that, is, okay, how to bring the technology that we have today to the ground, to talk with the people. I was hearing nice words, leadership, things like that, and I would like to talk about the things that we can do now with the technology that we have available. So, cement grinding is changing trends towards decarbonization. Yeah. This is something that we know already. I don't want to go so deep into it. We know perfectly how much CO2 emissions we are causing in the cement industry. We are, let's say, with a lot of different information from different sources. So this is nothing new for us. And I'm not a chemistry guy, so I will not go in deep into this subject. The idea is to put only some figures there and to go deeply into the roadmap, 1.5 to DS. And here we have 3 or 4 clear fields, yeah? Why I'm saying 3? Because 3 of them is 97%. So in the thermal energy efficiency, we are already, as I said, I want to focus in only one here, because otherwise we will not have the time to talk on all of them. Thermal energy efficiency, we are already doing that with baby steps, yeah, and we're already done a long time ago, not because of CO2 emissions, it was done because of cost. So you wanted to reduce your cost in the cement plants, so we are talking about mill internal separators, small steps in the plant that you were bringing into a more efficient system. Fuel switching. As Christian Pfeiffer also, we are into the fuel switching starting, to be honest. We have a really close project here in Sharjah Cement. We were introducing wood chips into the precalciner. But honestly, we are also in baby steps. Then I will jump to the other one, that is innovative technologies, including carbon capture. So this is the biggest step, yeah, and where we have most of this roadmap. And honestly, this is something that I was talking with a plant director. It was very funny. He told me, seeing this for me is like in my personal life, like doing diet, he said. I'm seeing the 20 kilos that I have to reduce, and I see it so far away. But I'm not doing what I have to do. I'm not starting for the first 3 kilos. And this is where I'm seeing that we can start. We can make that kind of steps. As I said, you were openly talking about leadership changing, bringing the things to the ground. Yesterday, a takeaway message was like that, yeah? What we can do to bring the things into the ground now. And there is where I want to focus in my presentation. This is the reduction of clinker to cement ratio. There are a lot of things. Calc and clay is the last topic since years, and I'm seeing that. I was starting in Christian Pfeiffer working in South America, and I was seeing that in Argentina, in Colombia, and in Brazil mainly, with different technology. And now you were saying something where to fit that calcined clay into the system, if in the separator, in the mill. Of course, it depends on the granulometry. Yeah? So it depends on how it's coming, yeah, the calcined clay, because we were helping in that project. But important is how to reduce the clinker, as we know now, with other cementitious materials. Yeah? We have slag, we have fly ash, we have pozzolan, not in all the markets, but I was seeing that how it was implemented in the last time. So OPC clinker-based production is, let's say, part of the past. We are looking into the future with cementitious materials, low-carbon cements. You know perfectly all the options that you have in the market, different possibilities, but all are coming to the same, and this is where I want to bring the things to the ground. And I think that, okay, as Christian Pfeiffer, we think that we can be a partner for that, and I will present 2 cases of studies, practical cases, where we were able to do that, changing the separators, for example, is one of the things. Many of you were coming through our stand and you saw, for example, ceramic grinding media, intermediate diaphragm, things that we can help to reduce energy consumption, but in this case is purely clinker reduction. This is a case of a separator change in Germany. We are talking a plant that is nearby in Beckum, nearby our facilities, and it was a first generation to third generation separator. The funny thing here is that I said, I was going into plants doing mill inspections. Normally, we see each other here with a suit, nice. Normally, I'm full of cement. Normally, I'm in the plant doing mill inspections, doing audits. I see many known faces, and many of the known faces, I knew them through my ex-boss, Mr. Pichelmeier, that you might know, but he was traveling a lot here, and he was all the time going into the mill, and I'm doing the same. And I'm finding when we are doing audits, that the performance of existing separators, even third generations installed in the last 40, 30 years, is not a state-of-the-art separator. The third generation separator is still state-of-the-art technology because it was not changing. The way that we are splitting the particles inside the separating zone, inside the separator, was not changing. It's a rotating cage and guide vanes pushing the air. We are doing like circumferential speed with the rotating cage, creating centrifugal forces, and due to physics, the separation is happening. But the third generation separator in the last 40 years was changing a lot. And it's still called third generation, 3.1, fourth, whatever. Marketing is marketing. I'm more technical, yeah? The thing is that we can change a lot changing the separator. And we are talking about what we will do in 30, 40 years, but bringing things to the ground. I'm telling you that 70%, I don't want to exaggerate because it's a different measure, yeah? But 70% of the mill outs that I'm doing have a very low performance on the separator. So this is a relationship in between the particle size distribution that we are seeing as a retain on 45 microns, 63 microns, it depends on the measurement that we are using, and the blame. This is a case of a study of this separator. We were changing, I don't know if I have a laser, no, okay. So as you can see in the top right, it was the product that they were producing when they were with the first generation separator. You see that they were working mainly on blame. This was a measurement that they were using, less and less using the market due to the cementitious materials that we were using, and it's giving us a high surface, so the blame is a little bit fake sometimes. So here you can see that we have a 4,000, 4,100 blame, but the residue, in this case 63 microns, is 6.5 to 8%. They are changing the separator and keeping the blame. What is happening is that automatically the residue is going really down and the cement strength is going up. What you can see in the left is the commissioning, how it was done, all the tests that we were doing. Yeah, and I will go to the next picture, but before going, one more thing is that this is a first generation against third generation late state of the art. But we were seeing in many cases where you have second generation or third generation that this area there in the top right is going a little bit down, but not matching the latest state-of-the-art separators third generation that are more in the bottom side. So this relationship, blame and residue. So you can see here what was happening in that case. The first generation separator was producing, let's talk in tons per hour, 100%, yeah, or 100 tons per hour of that product. When they are changing the separator and going to the next step, that is 4,100 blames, you see the residue going below 1%, but the cement strength is booming, it's going up really fast, 31 and 59 newtons per square millimeter. The production was going up 10%. At that point, the plant was able to decide what to do. They decided at that time, that was done 5 years ago, no, I'm lying, that was 8 years ago. Corona time is making me lose the timeline, yeah? So the thing is that 10% was increased the production, and at that time they were saying, no, okay, I want more production. So what they were doing was adjusting the blame in order to match the cement strength, and the production was increased by 20%. Let me tell you that most of the projects nowadays are not like that. Most of the projects, when we are in this 10%, they are going for clinker reduction. So they are adding limestone, putzland, whatever they have on hand to reduce let's say, to reduce again the strength to make the cement at the moment, and up to 2-3 years ago, it was cheaper. That was the main aim. And nowadays, CO2 emissions. But it's the same. We are trying to make a better particle size distribution in the end product to reduce clinker factor. A second case is a plant in Central America. This plant had a third generation separator. And here is where I'm saying how important are small things. Third generation separator, but what happened is that most of the plants done in the last 30, 40 years with this third generation separator were calculated for not such a high blame cements. Yeah? So the circulation factor was changing, the recipes were changing, the moisture was changing, everything was changing, and it's doing that. The separators have a different relation in between feed and final product. What is happening at the end is that I will go directly to the trunk cores. You see, core cement, they were producing a GU cement, general use, general purpose. Core cement, you see the difference in between before and after. I don't know why part of the slides are missing with the headers, but okay. So you can see that the difference in between before and after is not a big change. So we are going into core cement, 3,000, 3,200 blame, not a problem. But what happened when we're going in the same case to finer cements, above 4,000 blame? And if we are doing with kind of pozzolan limestone that is giving high first surface, we're going to 5,000 blame. You can see that in the same separator, they were struggling for new cement types, and it was third generation separator. Why? Because the feed into the separator was much higher, and the separators are not prepared for that. If you are over 1.7, 1.8 kilograms per cubic meter of air, the separator will collapse. And then the whole system is not collapsing, it's working, but the specific energy consumption is not good. But again, the particle size distribution is not good, and the clinker ratio is not able, we are not able to reduce it. Yeah? So, okay, here is the result, yeah? And here you can see third generation against third generation. I know that the circuit was not optimized, this is clear, yeah? But 27% increasing of production is a crazy figure. Together with the separator, we were changing also the intermediate diaphragm, another forgotten technology that you are using normally to replace, let's put a diaphragm, it's a mechanical thing. It's not a mechanical thing at all. You can improve from 7 to 14% the energy consumption on a mill, only changing a good diaphragm. The diaphragms are the same as the separators. They are technologies, first generation, second, third, and fourth. Nobody knows that, and this is very important. And at the end, nearly 20% less energy consumption. This is a huge step, but again, what you are not seeing here is the possibility of reducing the clinker. So this is the key figure for me here. How it was done that? I don't want to go so deep into the technology behind and the particle size distribution because it will take 1 hour, time that we don't have. So I will try to focus in the main topics. It was redesigned, the separator third generation. I insist, there is third generation, the way that the particles are divided. There is not existing any other technology more than a cage and a guide vane pushing the air and the particles through the rotating cage. But we were changing the shape with the computational fluid dynamics and making that the parameters inside the separator are more homogeneous. So that is more constant, the way that we are separating over the whole circumferential of the cage and the whole vertical cut of the separator, yeah? At the end, one important step, and I will summarize that in this slide, is on the right side, you see the new generation, and in the left side, you see the old generation, third generation. I don't have the pointer, but okay, sorry, let me go back. So you have the guide vanes and the rotating cage, the same as there. The difference is very, very small, but it's making a huge impact in the way that we are gaining on the particle size distribution, and it is that we have a 1.8 kilograms of material from the top, and nowadays, as I said, even more. So what we are doing is that feeding a lot of material from the top in the separator is doing that the air trying to come and go through, it's finding a dust, really dense amount of dust and very difficult to go through, and the air is going through the easiest way, so it's going from the bottom. Because the material is going to be filtered into the separator as per 0.8 kilograms per cubic meter. So as we have a big amount going out and a small amount keeping as reject, the air will go through the bottom. So what we were doing is designing, and this is very sensitive because I saw many trials, like trying to do it manually and it's not working. This is very sensitive in how much surface we give to the guide vanes or stator, or how you wanted to call it, but in the guide vanes, we were giving more safe surface to create the pressure drop enough to compensate the amount of material. Besides other things, you see backward inclined vanes on the separator rotating cage. There are many, many small things. As I said, it's taking too long, but the message is, with small changes on the third generation separator, you are creating a much better separator, better particle size distribution, allowing you to reduce clinker factor. And this is nowadays. And compared with the big projects, this is peanuts. And this is something that we can do now. Yeah? Me, being on sales, I'm always tempted to go to the big projects. But I think that this is giving us a lot. And this is something that we can do now in the existing plants, not only for the future projects. Yeah? So, do you need a partner? We are giving solutions. So, service, we have a pilot plant. I'm running out of time, so I will go very fast. Laboratory, so we are trying to now increase the amount because we have such an amount of samples in our main house in Germany that we have to increase the capacity of the pilot plant. We can do grindability, particle size distribution, density, moisture, all what is needed to try new materials. And believe me, the amount of cementitious materials are not stopping. So it's like coming bigger and bigger the list. So in all of that, we can help you. But again, I try to bring the things to the ground, and I said, okay, there are 2 or 3 key components that helps you to reduce energy consumption and also particle size distribution to reduce clinker factor. Yeah? So this is our pilot plant, grinding, separation, and pelletizer for other industries. And yeah, thank you, and I hope that we can have other discussions later on.
Thank you, Francisco.
Welcome.
Anyone want to come in quickly? While you're thinking about it, let me just check with you, because you put up that slide twice. You need a partner to create solutions. What is it about a partnership which produces the solutions?
At the end, we see this not as a supplier, not as a competitors. I'm seeing that more and more in the industry, that we are working together. And with the customers, as they are trying new technology, we are trying to be partner for them, trying to create a partnership, because we are also interested in creating these kind of new experiences.
Are you saying that progress is much more difficult if you do not have a partner?
At the end, this is something that we can be only a supplier if you have a clear technology that you want to use, but without having a partner in new cementitious materials that are very difficult to determine which one is applicable or not to reduce clinker factor. Without a pilot plant, bringing the material to the right particle size and having the state-of-the-art separator to do that is more difficult. So we like to say that we are a partner in that way, that the people can trust on Christian Pfeiffer, put the things in our grinding plant, in our facilities, and bring the last end product and put it into the cement to see the reaction.
Right.
So,
anyone want to come in?
One question.
Okay, right at the back, yeah.
Yeah.
Okay, could we make them questions quick, please?
Yeah,
so we can get as many as possible.
Yeah, okay. One question is the new design separator. What is the efficiency of the separator?
sorry,
Efficiency of the separator. Efficiency. Yeah.
Efficiency of the separator, okay, it depends on the kind of product that you will do, because this is a very sensitive due to the fineness. Now we are selling separators for 7,000, 7,200 blame. The last one was 10,000 blame for a specific product to blend it later on. As I said, there are so many topics to talk about. When we were talking about this 37% part of the roadmap, is also the blending. And more companies are interested on doing blending, and we're going up to 10,000 blame. So the efficiency of a separator is also run by the kind of product that you are, let's say, grinding. So it's a question that I cannot answer. It's, you know the figures from first, second, and third generation. This is written in every literature. But nowadays, we are out of the literature, going to this fineness and to these unknown products with different densities. So the efficiency of the separator, it depends a lot in the product that you will do. Fineness, density, and many other things.
Good question.
One more. Please quickly, I'll ask you one question. You said that low blane and low residue, that is low blane and low residue. Second thing is high residue and high blane. Okay. So the first high blane and high residue, there will be a strength variation, no? For both. Anyhow, you are just reducing the blane and increasing the output. In the first case, and second case, you are reducing this blane also and this residue also. But there is a variation in the quality of this cement, no? Because generally cement at higher blane will give a higher strength.
Yeah, I don't know if I got all the question. It was long. I'm like, I have kids. I'm like Nemo in, Finding Nemo. I'm forgetting things quickly. But I will try to focus in the main topic. At the end, this relationship in between blame and residue that we were talking about, it was one case. As I said, you are going into finer material more split it will be. You're going into more new technology, more together it will be. Then there are many other factors. But finally, the blame as a figure, it's losing a little bit of power when we're going to cementitious materials if they are easy to grind. If they're hard to grind, not. But as a common figure, we're trying more to go to the residue. And a separator, coming back to the point, I don't want to distract. Coming back to the point, a separator with high efficiency in the blames or residues that we are running today, it should be below 10% the bypass and imperfection again. I don't want to talk about imperfection because this is the sensitive point depending on the material. Okay. But bypass should be below 5% even.
Thank you. Right. Keep the
Thanks,
question
Nick.
short, please,
yeah.
and then here.
Very short, a couple of comments. Francisco, I'm very glad that you showed this relationship between blane and residue, yeah? At the 45 micron especially. Because I know this is one of the low-hanging fruits. And when we talk to our manufacturing, they say, no, this can't be done. We can't get the residue below this and this and this and this. So that's fantastic. So you can get a better strength, a better performing product with a low blane if you are managing your residue right with the right kind of separator. That was the message, right? My point, my question to this thesis is, have you done a cost-benefit analysis? You said existing plants can put on this new separators, third generation or whatever you call them. Have you done a cost-benefit analysis? Like say, for example, I'm able to get a product faster because I'm grinding lesser and my residue is lower still, so I can live with that. But I'm able to have a better output. You showed 100 TPH versus 120 TPH. And then what is the cost benefit on this when I put the capex for this new separator?
In that
modification,
case,
the modification.
Yes. In that case, they went back to the 10% practically. They were back in time. They were back to grind a little bit coarser. Yeah. Sorry, they were back on the blame. Yeah, to the 4,100, coming back to the 10% only increasing of production, and then they were changing the clinker factor, trying to achieve a lower clinker factor, but maintaining the strength. For that, they are losing a little bit of production, this 10% extra reaching the 120. And at the end, they were able to replace clinker by 3–4%. This is what I'm saying. We are talking about bigger figures, yes, I know. And I like the presentations that I was seeing, really professionals. I mean, from my point of view, when I saw the roadmap that Amr was presenting, and he was presenting all from MENA, and he was presenting as a second step efficiency, optimization, all of that. Even, I tell you, bolt charge. Every time we were changing a diaphragm, and we're seeing the bolt charge that they have, is 30% of the efficiency of the mill. And 80% of the market is running on ball mills. So I know vertical mills, lower efficiency, but we still have a lot of ball mills in the market running with third generation separators or second or first or third very poor, wrong dimension at the time of doing the plant because of whatever reason. So we have a huge potential in the existing systems and making the first step now.
Right, last question.
Yes, Francisco, Philippe Lavec speaking. Just, given, the increased use of ternary cements or blended cement, wouldn't you advocate for separate grinding to get more efficiency, both on energy and CO2 reduction?
From my point of view, the best is to grind and separate, splitting the materials, and then making the best out of both of them, mixing it together, blending in a mixer, and sending it out. The problem that we are having and facing now is that most of the companies, again, we are going into CapEx, and then they are saying, let's save one separator. So they are putting the grind material, in one shot, that is sometimes fine enough, into the separator, as I was hearing before, where to put it, in the separator or in the mill. And then there are a lot of options. The perfect option will be make a ball mill efficient for one kind of product, the other one for the other one, maybe OPC cement, and then you have here the other cementitious material, supplementary cementitious material, and make a circuit for that, giving the best particle size distribution for that product and mix it later on. This is the most efficient, yeah? as I said, there are a lot of options, but this is the most efficient in the market at the moment for doing it like that with separate grinding and separating.
Francisco and Adil, thank you very much. Adil, thank you very much indeed.
Thank you very much.
For your contributions, and thanks for all the questions. We could keep going, but we've got to move on in order to get you to lunch at 1:15. It'll not be 1 o'clock, it'll be 1:15. So can I ask you to leave the platform? And Apoorv, come and join us, and Tom, come and join us as well, because we want to keep driving this direction of travel. And Apoorv, you're going to talk about improving the performance. We were just hearing from Francisco there about improving the performance of cementitious materials.
That's correct. Yeah, I have a few slides to go through as well, Nick. But yeah, I serve as the CEO of Carbon Upcycling, which is a Canadian carbon tech company. Most of our work, as I'll talk about here briefly, is about improving the performance of SCMs, but also reducing carbon emissions directly. So carbon upcycling, for some of you that might, or many of you that might not be aware, it's a carbon utilization company based out of Canada. We started 8 years ago, primarily focused on nanomaterials for use in advanced polymers and composites. But about 4 years ago, we participated in the Lafarge Holcim Accelerator program and realized that our catalytic process can actually be modified for improving SCMs. What we especially found really exciting was that this could be scaled to be cost-effective and can work not just with industrial byproducts, but with natural minerals such as mine tailings from nickel mines and diamond mines and things like that as well. And I'll talk a little bit about that in the context of kind of why it was easy for us to make the shift towards cement. You know, a lot of people have talked about the 8% emissions globally that come from the cement industry. You know, not a fan of quoting McKinsey a lot, but what was interesting with their analysis was that they found that for per dollar of final revenue in the industry, cement was actually the most intense from a carbon perspective. So for every kilo of cement versus a kilo of steel or whatever else you buy, there's a pretty high carbon footprint that goes with that. And an interesting dichotomy, which maybe isn't as much of an issue in the MENA region or in Asia, but is becoming a huge issue in Europe and North America, is the staple SCMs that people have been relying on are actually going away at rapid pace. And what's happening is that as the supply is going down or kind of becoming less abundant, the demand is showing itself to be inelastic. And so as the steel industry electrifies and goes to electric arc furnaces, as coal power plants are replaced by natural gas plants, the cement industry could potentially be in a spot of bother in the sense that the SCMs that you rely on to decarbonize your current production to get to the high clinker substitutions that are common in China, India, and elsewhere could actually be going away. And we're seeing that happen in many parts of the US and Canada. Alberta, as an example, where we're headquartered, it's a fly ash market. So you have about 30% of clinker displacement with fly ash. But now there's one coal power plant running in Alberta, and they have nowhere else to go. Like, they're trying to figure out how they can harvest it, how can they switch over to clays or basaltic rocks or something else. And that's really where our technology has shown itself to be quite promising. We have a pressurized catalytic milling process. We have a video that we can share offline with folks that are interested to learn more. But essentially what we've shown is that we can chemically activate the silicates and the calcia and magnesia in SCMs like fly ash or steel slags or other materials, such that they can directly sequester CO2. We've talked a little bit even this morning about abatement. Our solution has a sequestration element as well, and we're currently working with Verra as well as the gold standard to generate verified carbon credits for each of the plants that we're currently looking to deploy over the next 18 months. What's really interesting, apart from the sequestration angle, is the fact that we're creating a highly reactive SCM at the end of our process. So instead of just sequestering the CO2 and making something inert like an aggregate or a sand, we actually have shown that we can significantly improve the baseline performance of that SCM. We've taken some raw clays, we've taken crushed glass, we've taken steel slags, and of course, things like fly ash and mine tailings that have been talked about a little bit this morning. And what we've shown is that we can get them well above that 75% threshold in terms of strength activity, which is kind of the baseline table stakes for people to look at pozzolanic additions on site. What's been very remarkable about what we've been able to show with the 35 or 40 odd materials that we've tested so far is that many of these things are not just inert, they're actually, you know, if you do a 25% substitution of clinker as per an ASTM standard, you're actually seeing a reduction of SAI at 28 days. If you just ground up the material and mix it in. With our process, we're actually taking care of some of the crystallinity, some of the surface charge issues, and what we're finding is that along with that minor amount of CO2 sequestration that you get, you're also seeing significant improvements in the reactivity. We've been able to do two things over the last 4 years. One is scale up. So my colleague Natalie here is holding our beta reactor. This is the reactor that we built back in 2015 through a lot of kind and generous support from the Canadian government. The reactor that you see behind her is the reactor that we started using last year. So in May last year in Calgary, we started producing the lowest carbon concrete mix that was available in Canada at the time. We actually took mixes that were already 30% substituted with fly ash. We took them all the way to 45 to 50%. We did that with two of our partners in the space. Lafarge is a big player in Western Canada. They were one of our partners. And Burnco, which is a ready-mix company, the largest kind of independent ready-mix company in Canada. We're also able to file a lot of patents to make sure that the versatility of our process is captured and protected. And what we're now moving towards is commercial deployments. And I'll talk a little bit about that as we move forward. The one other thing I wanted to talk about, Mr. Ghosh yesterday talked about some naive entrepreneurs that might have some interesting things to say in terms of decarbonization. I think I agree that we're naive. And I think what has been really interesting and exciting is that now things are becoming more standardized. I mean, whether it be the carbon credit space, whether it be the cement efficiency, like clinker efficiency space, there's not a lot of standardization. So there's a lot of different people saying different things. The Minnesota Department of Transportation, along with the Highway Transport Association in the States, funded a study, an independent study of 12 most promising SCMs and or carbon tech solutions in the US and Canada. We were one of them, and some of you who are familiar with low carbon solutions in the cement space or concrete space might be familiar with some of the other logos here, like LC3 was also trialed in that as part of an Ash Grove project. What was really kind of gratifying for us was the 28-day results from that study came out last 2 weeks ago now, and we showed the highest clinker reduction in the final mix. In fact, we had the lowest embodied carbon for any of the mixes that were studied in that program. And a publication on this will be coming out in due time, which will further kind of show some of the durability impacts that our process has had as well. This is just this is actually the patch of the interstate that was done with our product. It finished quite well and showed superior compressive as well as flexural strengths. And what was interesting for us from this exercise was not just the fact that we're actually getting into a real project outside of our Canadian, kind of Western Canadian deployment at this point, but also the fact that we actually think that concrete can be a very exceptionally carbon efficient solution if low carbon technologies are incorporated to lower the carbon footprint of the material. Like when we look at the broader ecosystem of other materials like asphalt and others, we actually think that by being progressive, there was a talk by Ehab yesterday who was talking about opportunities, not just risks, and we see ourselves as being able to show in tangible terms how those opportunities can actually be used to grow the market share of concrete in the world and make this an opportunistic story as opposed to talking about the negatives about how many emissions there are currently. So I'll just finish quickly by talking about some of where we've gone. So I showed you a picture of our commercial demonstration reactor. If you guys are brave enough to come out to the Canadian winter, please come out and visit us. But we are going elsewhere as well. Like we're seeing that this supply chain issue is growing all around the world. And just as of June this year, we received some funding from Innovate UK along with our partner and investor CEMEX, where the plant in Rugby, just outside of Birmingham, is going to be using crushed glass, using that as both a carbon sink as well as a reactive SCM to displace some of the clinker. They currently import fly ash and even blast furnace slag from Spain or Italy or Turkey. We're giving them a local solution that has to travel less than 40 miles. And of course, along with the fact that we'll be replacing clinker, some of those transportation-related emissions will be avoided as well. And they're not the only ones looking at this. We've got a couple of projects. We're looking at a project right now in California where an engineering study is underway. We'll be deploying a full-scale commercial project at a ready-mix plant in Canada before the end of Q1 next year. And with one of the other 3 largest cement companies in the world, we'll have a project in Ontario, which is actually the biggest cement plant in Canada that we'll be announcing fairly quickly as well. Again, going back to something Ihab talked about yesterday, we have to look at this from a holistic sense. This is, I asked a question from the PwC guy yesterday about kind of how we look at decarbonization in cement in the purview of everything else we have to do as an ecosystem in society. Creating more optionality in supply chains. There are very pozzolan-rich markets. There are fly ash markets, blast furnace slag markets. We think that by 2030, you need to have a plan A, B, and C in case your staple SCM starts to disappear or become a lot more competitive to source. By creating a carbon credit revenue stream, by creating a cost-effective way of taking low-grade SCMs. The LC3 colleague earlier mentioned how kaolin content has to be above 40% for some of these clays to be effective. We've started some work with a couple of tech research centers where the kaolin content can be in the 25 to 30% range to see if we can explore that as well. And I think, whether we are successful in that or not, we think that optionality generally is something that large cement and concrete companies have to pursue quite actively. And I'll just finish by saying, when we started out 8 years ago, our target wasn't the cement and concrete industry. But what we do see is that because of the high volume, low margin nature of this, we've already started to make a lot of strides where, players like the city of Calgary, as an example, have started to use our product in sidewalks and other non-structural loads in record time, like in less than a year of our product being in the field. Our vision is to use the cement and concrete sector to become the most impactful carbon tech company of this decade. There's been a lot of talk about how the 2020s are going to be a very important time for us to put a lot of these balls in motion. We're very excited about looking at partnerships across the world to make that happen, and would love to talk to anyone who's interested in looking at that in the short term. Thank you so much.
Tremendous, Apoorv. Anyone want to come in? I've got a couple of questions, but anyone want to come in immediately? Okay, well, while you're thinking about it, and Tom is going to talk about zero carbon elements in a moment, continuing this theme of producing concrete with zero emission cementitious materials. But Apoorv, let me just pick up, you kind of dropped it in at one point, a generous support from the Canadian government. How important is that when it comes to the numbers?
It's huge at the early stage. We're still not producing.
Could you therefore not have made the progress had it not been for the government?
Absolutely, yeah. I'd probably be working for another startup or something like that.
Because that's important for everyone out there to understand, that you need that security and you need the cash.
At the early stage, I mean, even if you look at the history of innovation like Xerox PARC in the iPhone sector, or like you want to call it smartphones and things like that, every sector that has been able to disrupt and make fast change has relied on essentially a benefactor that's able to take a time horizon of 10 to 15 years to see that translate into real action on the ground. So I absolutely agree, Nick. I think what needs to happen generally is there needs to be early stage grant money or some kind of non-dilutive capital available for people to take some risks.
Was that a hard struggle to get it?
In parts. I think generally speaking, getting out from academia into the real world is generally tougher because I was having a conversation at one of the breaks yesterday where we talked about how we're looking at 100 or 200 ton a day facilities over the next couple of years, and the first question the guy from industry asked is like, you mean an hour, surely? We said, no, like day, like this is still small, it's gonna take time to grow. And I think there's a phrase I heard a sustainability director at the city of Vancouver say a couple of years ago, like where they said, we underestimate what we can do, or we overestimate what we can do in 1 year, but underestimate what we can do in 10. I think especially in heavy industry, whether it be steel, cement, fertilizers, one of the things that we have to look at, and I would urge all the institutional players to look at, is to consider, taking small bets. You don't have to go, right away and start looking at 100 or 200,000 ton a year facility to really demonstrate the project and its viability. If you can take smaller but more bets, you're going to learn a lot from every step. And yes, the unit economics aren't great. The economies of scale doesn't kick in at the small scales. But that's where government support and a more progressive direction from a policy standpoint can be instrumental.
Before we go to Ricardo, my next question, based on that image you had of the Cemex plant, I don't know where it was it in
Rugby.
Alberta? That was in rugby, was
in the
it?
UK,
Okay.
yeah.
But I'm just very conscious, you know, you come from a country which, in theory, is very pollution and sustainability conscious, in theory. But you're based in Alberta, where you've got the tar sands. How much is what you're doing driven as much by public perceptions, public anxieties? In other words, they're not prepared to let you get away with stuff.
Not very much. I would say, again, it's a case-by-case thing. So,
But in Alberta, you feel under pressure from the tar sands.
the oil sands, yeah.
Oil sand, same thing.
Yeah, yeah. There's a bit of a PR battle going on, so I have to stay true to my new home, I suppose. But no, I think you're right, Nick. Like there is definitely pressure from a policy perspective, and some of the agencies that are, you know, in charge of taking the carbon levies and decarbonizing and all of that. Like they're definitely more keen on looking at ways to change the public image. I would say that's much of the world, though. I mean, if we think about you know, some of the projects we're looking at, even in Southern California, I mean, 90-odd% of the cement plants in the world still burn coal and petroleum coke. You know, Ontario in Canada is one of the more progressive places where hydro has taken over most of the grid, but there's still coal power in Alberta or in Ontario, like it's just at cement plants and at steel plants. So,
but what I'm trying to get to is when you're making the calculations and the policy decisions, how much is that a central part? We're not just talking about the developing world, we're talking about the developed world where there have to be these changes.
I would say it very much goes back, you're asking about the variance there, right? Like how much more progressive, and I would say
sensitive.
Fair, yeah. I would say it's hard to say because we haven't had any projects in the developing world yet. So it'd be interesting to see where that is. But I do agree that I think Alberta has definitely been progressive in that regard in terms of supporting us and a few other companies. I think one other factor there too is diversification though, which is away from just, you know, the bad image of the oil sands. I think it's, you know, when you're just focused on the energy sector and you're trying to look at other ways of making sure that, you know, if there is a crash in the oil prices like we saw even a couple of years ago, like, you know, when the price of oil in the financial markets went negative, do you have something else that you can rely on? And Canada as a whole is a net exporter of cement into the States. And so if you can provide a low carbon building material which is segregated from the oil sands, like that does become a pretty interesting way of looking at it as well.
Okay.
But yeah, I would say you're right. Like there's definitely a sensitivity there. And I guess we've become good enough at leveraging government support that we know how to milk that.
And you said the Canadian government, not the provincial government.
Both, yeah.
Okay.
We've been lucky with both, yeah.
Ricardo, last question, and then we'll go to Tom, please.
Yeah, very quick on, I think you've mentioned carbon credits. You mentioned Vera or similar. So maybe that's something worth elaborating a little bit if we have the time, because that could create some value for this audience potentially. And I was particularly interested to be very specific on if your customers are getting credits potentially from the CO2 which is sequestered into the SCM or from you know, the SCMs themselves, how much you use in cement. Thank you.
Yeah, so it's a mix of both. So carbon credits right now, if you look at any kind of renowned registry, there are a lot of crappy carbon credits out there. But if you look at the registries that have actually another Brit, like the Jamie Oliver thing a couple of months ago, did a really good job of kind of calling out some of the hypocrisy in that. But there are carbon abatement credits, which is just displacing clinker and showing you're getting more efficient with your materials. And then there are carbon sequestration credits, which are valued at a lot higher value. I think to your point, like when we look at business cases and even the way we're looking at our secondary pipeline of projects outside of the 4 or 5 that I mentioned on stage, what we're essentially saying is that there is a lot of capital wanting to get deployed in this space, especially if you can show the green factor, if you can show that there is a way of becoming more carbon efficient than is the case today with the baseline. So in that case, what we're doing with each of our partners is we're actually splitting the carbon credits we produce, both the abatement and the sequestration. And overall, you know, there are good ways of doing that. There are best practices that have been established. And what we're thinking is we're looking at the Gold Standard and Vera as the 2 registries that we think are probably the most kind of up to speed in terms of the monitoring protocols, the verification processes. And yeah, by middle of next year, at least 1, if not 2 of those projects will be verified and generating credits. And we can backtrack that as well. So even if we start generating credits before it's verified, we can go back and claim those. And yeah, like, you know, given the low margins in the space, they actually do make a difference. In areas where you have good clay deposits or mine tailings or some other material that you can upcycle, it makes that much more sense, and it can actually improve your rate of return quite significantly. But ultimately, our aspiration is to say, in 2025, 2026, if you're trying to increase your cement capacity, do you want to build a kiln where for the next 30 years you have to burn a fossil fuel? Or would you look at some other way of using an all-electric process, potentially a process that can use local wastes and create a local circular economy? Our kind of thinking and my professional career bet is that people will choose the latter. But that's definitely where we want to focus right now, is just to de-risk the tech where, when you're getting a loan from someone like an EBRD yesterday or someone else, you're looking at an electric process as opposed to something that requires heat, or at least a significant portion of your production is coming out of an electric process.
All right, thanks. Electricity is suddenly becoming more expensive, though, in most parts of the world. Okay, Apoorv, stay there. Tom, answer the question. Zero carbon cement. Do you want to stay there, or do you want to go here?
I can go up there, but we just amended that from zero carbon emission to zero clinker, actually. We're not yet to the targets of
So
net
do I
zero.
need to change this?
You can change that, yeah,
Okay.
you can. And but it's not the zero carbon emission that we are now, but we actually already targeted the 2030 goals of carbon reduction. So when we all struggling to get into the under 500 kilos per ton of cement target, well, we have technologies that reaches to really today 200 kilos per ton. So thanks for your attention. Reaches goal, so I can go now. Job's done. So thank you for receiving us here. I'm happy to do this first presentation at the World Cement Association for us. It's quite important because as we do not use clinker, we're kind of outstanding of the cement world and therefore not always called as cement, but that's what we actually do. How we did it is basically having a thoughtful thinking on the clinker itself. We try to reduce clinker, which is obviously a capital today. But what we did is we thought it's different ways. So what we get rid of clinker and see what's left to actually create new cements. So you basically know, obviously, all of you, how a cement production plant works and where the CO2 emissions come from, quarries, kilning, blasting, and so on. What we're seeing on the left-hand side is our H1 pilot plant that was built in 2018. And as you can see on it, there's no quarries, no chimneys, no kilns. So basically, we're not using any fossil energies to produce our cements. So the impact on that is that we're reaching now under 200 kilos per ton of CO2 cements, okay, that are already available in our plants. You'll see just afterwards our second plant. The first one, the pilot plant, is able to produce 50,000 tons of cement per year. It was our pilot plant dedicated to test on industrial level what we could do in our labs, what David Hoffmann, the creator of the technologies and the activators, could do in his lab. That will change a little because, as it was said previously, the steel industry is going through changes, and we've got an allocation now of 1.4% of their carbon footprint to add to our technologies as well. That's for the slag technology anyway. What we can say today, again, I'm jumping on the previous presentation, is that we're going fully electric. Do you want to invest in a 30-year plan to burn and use a kiln rather than using electricity? Our plant is fully electric, and using all the solar trackers that we have around it, we actually produce ourselves 52% of the energy needed to produce our cement. Another important goal is that actually the energy consumption represents only 2% of our costs to create the technologies. So I agree, electricity is getting more and more expensive in every country, so having our own production capacities obviously helps us to keep a stable price range, basically, towards Portland cement, which is rising today due to the energy cost. These are the technologies we're discussing today. I'll focus a bit later, just afterwards, on one of them, which is the HUKR, based on blast furnace slag. Okay. Basically, what we do is always the same. We have a byproduct, okay, or co-product, always the same ones as we've discussed since yesterday: blast furnace slag, calcined clay, gypsums, and so on. But we're also working on different technologies such as biomass ashes for tomorrow's goal. Our idea is actually to find any kind of byproducts and co-products that could be used throughout the world and be able to activate those and produce cement on site. So that's how we do. We have HUKR on the blast furnace slag, HEVA for calcined clay, and HIONA, which is our first product that was certified under CE norm, because that's where we did our cut in our forward thinking, is that we added 0.5% of clinker in the formula to be actually called a cement and get that norm for that product. If I focus on the HUKR technology, which is the most advanced that we have today, it's an alkali activated cement with no normative standards, and so we had to go through the building authorities in France, because CSTB, to get some approval to it. So it took some time and a huge amount of money, as you can imagine, to get this standard, and we are now under 8XA. So basically, today our HUKR cement, which is lower than 200 kilos per ton in production, can fulfill any use, well, 85% of the usage of a traditional cement today. As you can see on the compressing strengths or a few mechanical and physical characteristics, we're actually reaching at least as good as Portland cement and sometimes even better. So we can see on 90 days we're reaching up to almost 65 MPAs. What you can see on the picture is our second plant. So you saw the first one, H1, 50,000 ton for around 15 million capex for it. H2 will produce 250,000 tons per year for an apex of 22 to 25 million tons. The idea of it is instead of having a horizontal production process using conveyors, we're having everything into a gravitational system using a blend mixing tower that was built by our partner Ibauer Hamburg. And if you take out the storage capacity, this will only take 300 square meters landscape. So you can basically have a mixing tower producing cement very close to any building or any major cities. Here you see where we stand. The project started in 2014, 2015 with the encounter of our CEO and David Hoffmann, the chemist. And since then, we obviously did an IPO to get some money. We had subventions from governments as well, from different European projects and so on that we did at early stages. But when we needed to scale up and stop being called a startup, and I totally understand where you're at the moment, and to go over, well, we had to go for bigger money. So we raised 100 million euros since the IPO in 2018 to build both H1 and H2 units. And then the partnerships had to go another route. So we're not looking anymore for kind of proving how the product works. We're actually looking for partnerships that can use the product. So you can see big names on it, such as Cemex, obviously, but Bouygues Construction, Eiffage, and all these ones who actually committed now through partnerships to use our cement in a certain percentage of their buildings, and that throughout the following years, which makes us today up to already more than 200,000 tons in our production order book. Other partners, obviously, are going now worldwide. Obviously, we're very French, so we have to go through the closest neighbors in the first place. So Switzerland with Molini, or Ecobat in Belgium, Semblend in the UK, who just signed recently for distribution partnerships. But for Switzerland, we actually have now our first joint venture to have a proper production capacity in Geneva also. So that's where we expand. We have to go through these borders, both to find partners to help us keep growing and keep supplying the product. And thank you for your attention. So I'll be open to questions, because I'm sure there'll be some.
Thank you, Tom.
Thank you.
That 100 million, did that cover your costs? What you raised?
Yeah, it did.
It
did in some costs. Obviously.
The reason I'm asking is,
yeah.
Was it enough?
It's never enough.
Well, what would you have liked then?
It's never enough. No, it was enough to, as I said, to build the H1 pilot plant, because we already had some funds for the laboratory tests, obviously, and we needed to see whether what we do in our lab can actually be reproduced at industrial scale. Otherwise, there's no point keep going. So we needed that money in the first place for that plan. So that's where the first million came out for that H1 plan. And since we achieved to produce the cement on industrial scale, we just thought now, okay, we have to produce more to be able to provide.
But have you created a model there which can be taken away by many of the delegates here? In other words, both in terms of cost, money raised, and also opportunity that creates?
Well, I wouldn't be the right person to talk about money raising because I'm not much into the financial
but you
raising
benefit from the money raised.
But we benefit from it definitely, and the model, yeah, because it's as I said, we're partnering with Ibao Hamburg, who are dedicated to these powder blending towers, and basically this model of the H2 unit, the tower, is what we want to replicate abroad. So we're having first a second tower unit being built in Dunkirk by the end of 2026 for another 250,000 tons to reach our goal of 550,000 tons production capacity by the end of 2026. We're having the same model be built in Geneva, again by 2026, and the idea obviously is to find these partners that are willing to either finance, either build themselves, either use themselves, this type of units to produce the cements where they are.
But what I'm getting at is, have you created a business template, which means that for that kind of price, you know what you're going to get, and it's very efficient and effective?
Yes, that's why we did. The H1 pilot plan was to test the product at industrial scale. The H1 pilot, the H2 plan, sorry, is the model that we want to duplicate because we know it works.
Okay, anyone like to come in, please? And yeah, we've got plenty of hands going up. Microphone at the front and further back, please.
Thank you. Arnaud Pinatel on Field Research. Just a question on the pricing of your cement, because we are hearing in France that I think this cement is offered at 200 euro per ton, which is almost twice the price of the ordinary cement in France. So all your clients are accepting this type of pricing? Because it's quite a significant gap. So I guess to penetrate the market, you have the benefit of the CO2, but you are pricing much higher than your competition.
Actually, it was even higher. It was 240 euros per ton.
Okay,
but but it's we had to go through that roadmap of pricing because we were into a startup system with that business plan, and we didn't have any volume capacity to cover up all these costs. So we have to go through high-end prices for a premium product to supply H1 facility. Now that we have the volume capacity, we're actually going around on a volume type of price, and we're going much, much closer within the following months now to what a traditional cement would cost.
Can I just pick up on what, sorry, do you want to come back in?
No, thank you.
But just before we move on, you did say Geneva, did you?
Yep.
That's interesting. I mean, what were how specific, how discerning were the canton about allowing this kind of thing to happen in a place like Geneva?
Well, the idea is that tower can be adapted to whatever quantities and you want to produce, so whether in height and width and so on. So the idea is to place it as close as we can from cities, okay? And the moment the challenge is not to actually find a partner or finding even the raw materials that we need or the core products, it's finding the right land to place it with accessible by rail, by boat and everything.
Because you're talking about a restricted valley there.
Exactly, yeah.
Yeah, okay, that's why I'm asking. I'm intrigued.
Yeah. Quite a very, very, very interesting technique and system and technology, honestly. And back to the economics, I think I missed the first part, but now it's raised by Arnold. So it's 200 euros approximately per ton. And you think your economies of scale can drive that to better economics later? So it's more closer, as you said, to what the market can deal with. So this is one question. The other one, from what I heard from you, the arithmetic say that it's almost 100 euro as a capex per ton. So a 1 million ton capacity would be at 100 million euro investment cost. Does that, did I read it right?
Well,
I didn't make
the calculation the other way around, to be honest. Again, I'm not into the proper
no, you said your 250,000
tons, yeah, for 22,
like 20
yeah,
million.
that's what it, yeah.
So that's quite sensible.
Yep.
as an investment cost.
Well, that was the
compared to
idea.
classical.
If you're going too high in CAPEX, well, you can only work on the technology, and it's already hard to convince all the people to go green, whether it's green or gray or whatever, depending on how they do it. All our products are under EPD sheets, so we cannot lie on this, and we're totally fully transparent on our carbon footprint. But it's already difficult to convince people to go green, so if it's even more expensive and not worth it, money-wise, they will never get to it. So we had to go to a program where, it was sizable in terms of CAPEX in the first place and investment on a long-term basis.
Thank you. Thomas, thanks, Nick. Yeah, I must congratulate...
You still have questions after all the talks we had.
No, I'm not asking a question, but basically, yeah, it's a question because, I'm sitting here with Roland. So we are ex-Guelzim people, spend our entire lives in the cement world, or Lafarge people. And then we find your thing very attractive. So if you have a solution, do you have a solution for ash as well? That means clinker made out of fly ash, alkali or whatever activated, without the need for, cement made out of fly ash without the need for clinker. So you have got two big clients here. We have plenty of ash.
Well, I'll have plenty of activators.
Yeah. and I mean, we would be happy that if our cement plants could be made redundant.
I understand. No, we as I said, we have three technologies, let's say, available today, like marketable and sellable today. As I said, we're still working on various different byproducts, like biomass will be the big thing for us towards next year, biomass ashes. And we did work on fly ash also, but back then was 2015, 2016, and we did trials with activators, and we managed to reach some good performances with it. It was just more a marketing choice not to work on fly ash at the beginning, because we were not seeing, let's say, a long-term or a very long-term strategic choice for us. Obviously, recent events made us think that different way. But so we are able today to activate some kinds of fly ash.
Okay, good. I mean, just to follow up on that, you mentioned about the marketing thing, right? I mean, Anne is not here, but say, for example, what do you think about if tomorrow we go to our clients and say, look, I have a cement which is clinker-free. What would be the take-up rate, or what would be, I mean, we can imagine how would people react to it, and what would be the time required to get this convincing done? Okay, you had shown some examples of Bouygues and other people who have started using it. But just thinking about, what is your thought on this? Like when we offer people clinker-free cement, they say, oh, is the building going to fall apart in the next 2 years? And then show me a track record of the last 50 years. These are obvious questions which we face. How do we deal with these kind of things? What's your thought?
Well, that's why we went through the route of certifying the product straight away. It's been a 6 years footpath to get there, and we had both to create a roadmap to certify our future clinker-free materials to get certification, but we also did all the tests plus some others to actually get the same kind of certification, which is called ATEX-A in France today, just to prove to everybody, basically, that we achieve the same mechanical performances and we're using the product the same way. If there is only one downside of it for now, it would be that obviously the cement industry have worked a lot on the different admixtures to reduce shrinkage, to reduce water, to reduce this and that and this and that. And this is the part where we still have work to do. We already did, but we still have work to do because we need to adapt all these admixtures to react to our activators rather than the clinker before.
Okay, I'm asking about the technical issue, okay, in this, because this is, it's one part of geopolymer, okay, so that you are depending on the blast furnace slag, which is not available too much to replace the huge amount of cement, okay, so that our way is to use the flashed clay, okay. This is constrained for the kaolinite content in the clay to be that flashed, okay. Also, I can understand the high price is due to the price of the alkali activators, okay. So it add large value to the cost of the making the cement. But my concern is two things: the kaolinite content in the clay and the curing temperature of the product.
What was the second?
Curing temperature of the product.
I didn't get that one.
Curing temperature, curing temperature.
Curing?
Yes, curing temperature.
Right.
Is it in the room temperature, or you have to activate it in higher temperature?
No, it's a cold curing process. So there's no curing at all within the production of it. It's when the cement that we produce is actually mixed within the mix design that is dedicated to whatever project that happens, that creates the reaction, and that's where it happens.
Yes, it creates the reaction, and it undergoes the reaction in room temperature.
Yeah, exactly. It's a cold curing, basically.
Yes,
system.
In the room temperature.
Yeah.
Okay, type for the kaolinite content.
I didn't get that.
Is it constrained for the kaolinite content in the clay?
Use the microphone there.
Yeah, it's for the
Microphone's come
particle
back
for
to
clays
you.
and also from the activator that we made. That's the main course. The main course of the project are the activators. That's why it's patented, and we have 67 patents at the moment pending for those, and that's where it all happens.
Okay.
It's fine, it'll work.
Thank you for the presentation. I have two simple questions. My first question, you mentioned that your cement can cover almost 85% from the application required rather than the traditional cement. Is this due to the limitation in the physical properties of your cement, like the strength, the rigidity, like this? And what is the amount of the remaining 15% from the application we cannot use it? Is it for the heavy construction required a specific physical properties of the concrete? This is my first question. My second question is, can we use traditional cement and mix it with your cement up to some limit to improve the physical properties of the final required concrete?
So, for the second question, no, we cannot mix with traditional cement with ours, because actually the clinker will prevent the reaction from happening with our activators. So very small amount of contamination of it will not amend the product for capacities, but mixing it as a full mix design product, that would prevent it from working. Regarding the 85%, it's both regulation process and strategic choices. Basically, we targeted buildings, but home buildings and offices and so on, where the concrete is mostly used. So we targeted these ones and targeted our certification towards these buildings, and that's why we're down to 85%. So indeed, we cannot go for now, at least not with the insurance of a regulation to go for superstructure buildings. However, we know from our labs that we can achieve much better performances that we actually do and that we're actually showing in terms of official data.
Thanks. Last thought before lunch, Matthias.
Yeah, thank you very much. Congratulations for this interesting innovation.
Thank you. Thank them.
Yeah. As I see it, you replace the heat treatment with a cold chemical treatment to achieve that binder. I have two questions. When you treat ashes, is there any limitation with respect to moisture or carbon content in these ashes? Because many of those ashes which are abundantly available are having a high carbon content. That's why it's hard to treat them. Is that also restricting your process? And the second question, assume you get calcined clay abundantly. What is limiting your upscaling? I guess the secret is in your activator. Is that activator in some respect anyhow limited in mass production or hazardous by some nature?
Well, for the second question, no. There's no hazardous products in the activator. Neither there is any shortage on any of the materials that makes it. That's the first thing. So when we actually discussing with partners whether they could produce these cements where they are, the activator part, whether it's in price or supply, is not even a topic. It really, the raw products, the co-products and byproducts are the real key. Like for any other technologies today, calcined clay, which has to have certain kaolin in it, and the blast furnace slag that has to be a very high quality one, and the blending talks that we had before is obviously a very important matter to us. Regarding the fly ash, all I can say is that we're only working with dry powders, so it has to be dry. But regarding the carbon embodied in it, that I won't be able to answer to you to that matter. But if you do, write to me. I know in our lab who would be able to tell you that.
Thanks, Tom. I'm going to call a halt for the moment because we're 50 minutes late for lunch and we've got to keep the timetable somehow this afternoon. Can I thank you all enormously, both from the platform and from in the well of the hall, for the contributions you've made. Let me give you a challenge for after lunch. What have you learned that enables you to propose new ways to reduce carbon and reduce costs where you work, in your company? What are you going to go away with? Help us understand that. How much has your perspective changed? Matthias said right at the beginning, this is not a threat, this is a real opportunity. I think both from the platform and from the kind of evolving views we've heard from among you, we've seen that there is real opportunity if you're prepared to not take a risk, but actually invest in the way that is possible. Ricardo asked the question this morning, what is preventing you from picking up on many of these new ideas? If you're still being prevented, help us understand why. If you've changed, also help us understand why. And let's hope that in the afternoon we can feed off each other and create a new forward momentum in line with the great ambition of the conference, which has brought you all here to the UAE, and the confidence to also pick up with some kind of radical new approach that you can go back to put to your board, to put to your C-suite, and see what kind of change is possible. There is this degree of conservatism still, which was highlighted in the opening remarks yesterday. I felt that the mountain has been moving here in the last few hours, so let's see how much further we can push it. Ian.
Yeah, thank you, Nick. I just had a very brief announcement. Looking at such a handsome and photogenic audience, we thought we would take a picture this afternoon. So we're going to organize that at the beginning of the tea break, so about 3:30. So, you know,
don't go away.
Don't go away. Comb your hair. Be ready for it. Okay.
But thank you. It's lunch. But Ian, it's lunchtime essentially. Let's try and be back here for 2:10, please. Thank you all very much indeed for your contributions, and particularly from the platform.